All right. Oh, sorry. All right. So I was thinking that today we could go ahead and review for the test. And then I think that probably won't take the whole time. So I thought that I could also get you started on maybe problems 3 and 4, or 3 or 4 of the homework assignment. Actually, problem 4 is the one specifically that I would like to take a look at with you guys. So let's start with a review. We started out chapter 3 by finally considering an operator other than UXX. All right. And we considered the operator LU equals UXX minus U. All right. And what we found is this posed no additional difficulties. Okay, and we can take all the methods that we developed in chapter 2 and apply it to this problem, to a problem with this operator. And we didn't run into any problems. It all just worked perfectly. Why was that? Why did this new term not cause us any problems? Okay, good. We just needed to show that this was self-adjoint. Later on in the chapter, when we studied Sturm-Liouville theory, we were able to look back and say, oh, just like UXX, this operator also has a weight function of just 1, okay? So at the time, we didn't know about weight functions. And because this one just also happens to have a weight function of 1, or in other language, because it is already self-adjoint, it posed no problems, right? And so this should then, oh my gosh, there's an ant on my keyboard. Sorry. Then we considered this operator. Okay, and this gave us trouble. And why did this cause problems? It was like crawling out from the inside of the key. It was gross. That's right. So not self-adjoint under WX equals 1. So it's not self-adjoint. And we were like, well, how much of a problem could this cause? And we went and we looked for the eigenfunctions, and we found that the eigenfunctions were not orthogonal. And then we were like, oh my goodness, what are we going to do? How are we going to do an orthogonal projection if the eigenfunctions are not orthogonal? It was just clearly going to be. We needed some new insight. All right. And we kind of then explored this idea of a weight function. And at first, we just said, weighted inner products. Okay, and we said, what if we could stick another function in there? And at first, it seemed kind of a silly idea, but we kind of played with it a little bit, and we found that there didn't really seem to be any reason why we couldn't do it. And so we gave this the name of weighted inner product. All right, weighted inner product of U and V times WX dx is U, V with a weight function. And we looked at the eigenfunctions of this operator here, this UXX plus 2UX. And they each had an e to the minus x in there, right? Given the appropriate boundary conditions from 0 to 1, we got these eigenfunctions. And it was these exponentials that caused the problem. And we said, you know, what if we allowed ourselves to have a weight function, and if I multiply these two eigenfunctions times each other, then I have an e to the minus 2x. And that e to the minus 2x is the reason that we didn't get orthogonality. So what if my weight function was e to the 2x, right? And at first, this seems sort of too good to be true. We said, yeah, okay, it makes the eigenfunctions orthogonal, but can we do that? You know, is that allowed? And then we explored and found that it also restored the self-adjointness of the operator. You could show that if that's how we define the inner product with that particular weight function, e to the 2x, then indeed not only were the eigenfunctions orthogonal, but the problem was self-adjoint, and the transform of LU was minus lambda sub n u sub n. Like all the properties that we previously associated with these operators in chapter 2 were restored when we did this. All right, and so this worked out really well, and we decided to sort of generalize that approach. Okay, so first we defined a weighted inner product, and then we defined Sturm-Liouville form. All right, and any operator we can put into Sturm-Liouville form 1 over W of x, P of x, Ux x plus Q of x U. If we choose our weight function carefully, and what we need to do is choose it such that the derivative of this term equals that term, which allows this whole thing to be an exact derivative and condensed into this form. Okay, and so this is really it. We have this sort of game that we play. We find the Sturm-Liouville weight function. We put the problem into Sturm-Liouville form. And once we have found that wave function, everything else proceeds basically as before. The eigenfunctions are not affected by the weight function. They have the same, we don't have to know the weight function to find the eigenfunctions. We can find them in the standard way. But once we have them, the weight function makes them orthogonal. And the weight function makes it such that the transform of LU equals minus lambda sub n u sub n. Okay, so in the end, it was a pretty simple fix. To just a second, I'll answer that. To deal with non-self-adjoint problems, you just find the weight function, and then you're good to go. You deal with everything the same way as you did before. In fact, you can look back on all the problems we did in chapter 2 with the operator uxx and say, oh, this was just the case where the weight function equals 1. All right, and so this isn't even, you don't even have to like think of two different cases. You can just put all of this together in the same body of knowledge. This is how we solve problems now. We put them in Sturm-Liouville form, and we find the weight function. And once we put them in Sturm-Liouville form, all the things that we want to be true, we know are true. We don't even have to show that they're self-adjoint anymore, because we proved that all Sturm-Liouville problems are self-adjoint. Okay, one of my problems is, how do you know if it is a Sturm-Liouville problem? Oh, that's, I think, what I was just talking about, that all of these problems are Sturm-Liouville problems. All right, and all you have to do is put it in this form, and any second order problem can be put in this form. And once it's in this form, you're done. And you've shown that it's a Sturm-Liouville problem, and you have found the weight function.
If I remember correctly, you want WA, the derivative of WA to equal WB?
That's right. That's right. So want WA prime equals WB, because that makes this an exact derivative of a product. Right, if this equals WA prime, then this whole thing in brackets, let me make one more line here. Then this whole thing in brackets, whoops, becomes 1 over W, WA UX X plus CU. And then I just let WA equals P and C equals Q, and I get this standard form. I mean, I feel like that's kind of all there is to say about Sturm-Liouville problems. You've got this one extra step. You find the weight function, you put it in Sturm-Liouville form. You know, everything else is the same. If you've got non-homogeneous boundary conditions, you need to remove those boundary conditions using a boundary solution, and then come up with an interior problem that has homogeneous boundary conditions. In principle, you know, you still need to check and see the different cases, although we use this thing called the Rayleigh quotient to show that if P is positive and Q is negative, then none of the eigenvalues are negative. So you can often rule out that possibility of having to check the negative eigenvalues. So really, there's so many good things that are guaranteed by Sturm-Liouville form that it's very valuable to show that it's in this form. All right, then let's move on to chapter 4, which was the wave equation. Or sorry, the diffusion equation. Wave equation is next. So we don't need to know Rayleigh's quotient. Rayleigh quotient. It's useful to know what it guarantees. I'm not gonna make you rederive it, but it guarantees that the eigenvalues are positive, and that's useful to know. You should be able to say, like, because of Rayleigh quotient, I don't need to investigate this last case to justify your not having to do it. All right, so the diffusion equation, right, had this form, ut equals, in principle, there's a constant here. I'll make it alpha. UXX, this is called the diffusivity. And then in principle, we have a forcing function, which can depend on space and time. And then as before, we've got our two x derivatives. So we have two boundary conditions. But now those boundary conditions in principle depend on time. And this could be u or ux. In fact, I should go back to this sort of awkward but more generic form. B1 of U and UX. And then B2 of U and UX. And then I see there's a little bit of chat activity. I'll look down there in a second. And then I of X, sorry, U of X0 equals I of X. Then we would have a Sturm-Liouville problem equal to 0 and a Sturm-Liouville interior problem equal to the forcing function. Oh yeah, I think what you're saying is, what if I have to do boundary interior splitting with a Sturm-Liouville problem? And it's exactly the same as it was before, right? The boundary solution, we typically want to satisfy L acting on U boundary equals 0 with, U boundary, whatever, equal to those non-homogeneous boundary conditions. It's important that we don't just get into the habit of making this UBXX equals 0. If the operator is the L of U is UXX, then that's what this is. But if the operator is like UXX plus 2UX, then ideally we want to satisfy UBXX plus 2UBX equals 0 here. And then your interior problem will, the ideal outcome is that this is LUI equals f of x, where UI whatever equals 0 and UI whatever equals 0, right? And this is the generic splitting, right? Is that you get the boundary conditions on this side and the forcing function over here in the interior problem. And in principle, you should be able to do this regardless of what the operator it is, right? Whether it's just UXX or whether it's a Sturm-Liouville problem or whatever. Like this is, in principle, this is always possible to set up. All right, so new features. Remember the diffusion equation. The domain of the diffusion equation can be pictured like a semi-infinite, I don't know, soccer field or football field or something. You've got your x-axis here, you've got your t-axis here, you've got 0, and you've got L. And so here at this edge of the domain is our boundary condition at 0. Here at this edge of the domain is our boundary condition at L. And because we have two x derivatives with two boundary conditions, one on each side, because we have one time derivative, we have one initial condition, and that lives here. And this is new at t equals 0 and spans the x-axis. Okay, so the initial conditions depend on x, the boundary conditions can depend on t, and the forcing function can depend on both x and t because it lives here in the inside. All right, and this looks like a big step forward in difficulty because now we have partial derivatives. But really, because of everything we've learned so far, we can just hit this with the transform. All right, we don't need to learn hardly a single new thing to solve this equation. We just isolate the spatial operator. We ignore the time derivatives over here, and we ignore the forcing function. Anything that doesn't have a u in it is over here, part of the forcing function. And we just focus on these spatial derivatives, which make up the spatial operator. We call that L acting on U, and then we find the eigenfunctions. And we then hit this with the transform. Somebody has like banging metal in the background. It sounds like the basement of Clements.
Oh, sorry, I forgot to mute myself.
No, it's fine.
I have construction right outside my window.
Okay. So we take this, we identify the spatial operator, we find the eigenfunctions, then we hit it with the transform, right? And what we invariably get is du n dt equals minus lambda sub n u sub n, right, plus f sub n of t. If that forcing function has a time dependence, then this will have a time dependence here. We can move this over to the left-hand side of the equation. Put it in standard ODE form. And then we take the transform of this, and then we also have to take the transform of the initial condition. We take the transform of anything that depends on x. And so we have to take the transform here. When we take the transform of this statement on the left, we end up getting un of 0, and this is going to be I sub n, where that's the transform of this function I. All right, and since I does not depend on time, it's the initial condition, then this is just a constant, whereas this forcing function here in principle can depend on time. I should also, I should say u equals ub plus ui, where the boundary solution, we completely ignore the time derivative, all right? There might be time dependence in the boundary conditions, but we ignore the time derivative, we ignore the forcing function, and we just focus on lub equals 0, just like always. And so really nothing has changed except that at the end of the day, instead of getting an algebra equation, this is what we got in chapter 3 and chapter 2. But the presence of the new term here in the diffusion equation, the time derivative, gives us a new term in our transform, which is du n dt. And it turns this transformed equation from an algebra equation into a first order ODE in time. And that's really the only difference. All right? Everything else is basically the same, except at the end of the transform, you get an ODE instead of an algebra equation. Okay? And so it's not so simple as just saying, oh, great, u sub n equals f sub n over lambda sub n. Okay, that's not true anymore. That would be the solution to the algebra equation. We have to solve this differential equation. All right, and so it's going to have this constant coefficient structure, which means you can guess e to the RT for a homogeneous solution. And typically your forcing function here is going to be pretty friendly. And so you can use method of undetermined coefficients to guess the particular solution. And then you satisfy your initial condition, which comes along with the time derivative. And so, you know, this is not trivial, but again, I like to think of it as, you know, going downstairs into like a basement workshop. You know, don't let the work needed to solve this ODE interrupt your understanding of the flow of this problem. This problem is exactly like the previous problems that we did in chapter 2 and chapter 3, except that when we go downstairs, we're no longer solving an algebra problem, we're solving an ODE. Yes, this T is the vertical axis label. This is called a spatiotemporal diagram. Just helps you visualize kind of what the solution looks like, what the domain of the solution looks like. Okay, and we did, you know, we did several examples. I think we did what, maybe 3 examples of this problem. And if you go back of diffusion equations, and if you go back and look them over, what I encourage you to do more than anything else is to see how the structure of the solution of a diffusion equation looks exactly like the structure of the solution of a boundary value problem, with this one exception that you have to solve an ODE instead of an algebra problem. If you can see that and understand that, that will be the biggest single thing you can do to be ready for the test, because really there's nothing new here. So for all of these problems, should we be checking Sturm-Liouville form to make sure they are self-adjoint? Sure, yeah, just like before. In fact, that's the perfect segue into what I want to do with the rest of lecture. Here is my spatial operator, right? I identify the spatial operator LU, and yes, I need to make sure that they're self-adjoint or that I know the weight function. Now, all of the example problems that we've done so far simply had as the spatial operator UXX, or maybe some multiple of that, like 2UXX or something. Okay, but that is an operator with which we are very familiar. And we know that it is already self-adjoint and it has a weight function of 1. All right. So because we already know that that operator is self-adjoint, all those properties of self-adjoint operators, automatically apply. But what I want to do here in the last 20 minutes or so is take a look at problem 4, which is a diffusion equation, but it has a UX term in it. And so we're going to have to combine these ideas of how to solve the diffusion equation with the ideas of Sturm-Liouville operators from chapter 3. And it's really not a big deal. If it sounds intimidating, it's completely not. It's just that you have to put the spatial operator, you have to identify the weight function of that spatial operator so that you can take the transform. I thought the plots we have been looking at were UX of t versus x. Okay, yes. When I plot the solution for you, we're typically looking at x versus u, and it's like an animation if it has to do with time. This is not the same thing as that. This is just a way of visualizing the domain of the problem. All right. So if this problem were a function of like x and y, then this would make a lot more sense, right? You'd have x and y, and maybe it lives in a square, 2-dimensional domain or something. Here it's x and t, which really is a 2-dimensional domain. It's just that one of those variables is time instead of space. Okay, but really it's a 2-dimensional problem. There's 2 independent variables, x and t, and so you can represent that domain graphically by letting x be one axis and t be the other. And if we do that, we get this sort of visualization of the domain of the problem. The solution lives between x equals 0 and x equals L, and then the solution lives between t equals 0 and t goes to infinity. Okay, yep, so this is just a different thing. Other questions? Before we take a look at problem 4. All right, well, let's take a look at problem 4. Let me go remind myself what problem 4 is. All right, so for 4b, we're going to assume that kappa and v equal 1. I should have let v equals 2, but v equals 1. Okay, it is what it is. So we're looking at the following problem. Right? And so what we saw in the beginning part of this problem was a derivation of where this equation comes from, right? And it was basically an analysis of heat flow. And we saw that this term right here comes from like a bar actually moving to the left, right? And so if I have a bar with a heat distribution and I am now moving it, then the motion of that bar is, say I have some cell that I'm interested in. The motion of that bar is pulling heat into the cell from the right-hand side and pulling heat out of that cell from the left-hand side. Okay, and when you factor that phenomenon into your derivation, you get this extra term right here, where you have an extra component of the time derivative that is equal to the spatial derivative. Another way to think of that is, suppose my temperature distribution looked like this. And I'm moving to the left because here the slope of U is negative. There is more heat leaving on the left than there is entering on the right, okay? And so as I move this temperature profile, my temperature is decreasing, okay? And it's gonna decrease at a rate proportional to the existing slope. Whereas if my temperature profile looked like this and it's moving to the left, okay, then my temperature would be increasing over time. Positive slope means positive increase in temperature over time, all right? And so that's where this new term comes from. And so there's, that physical explanation for where this term comes from, but it's also now very convenient from a pedagogical perspective that now all of a sudden we have this spatial operator. Okay, and this spatial operator is not self-adjoint with the choice of weight function W equals 1. So if we want to solve this diffusion equation, okay, this is actually called an advection diffusion equation. Advection refers to the phenomenon of heat moving because the medium that contains it is also moving, okay? So this term here, the UX term, is called an advection term, not convection, but advection. And this term right here is called the diffusion term. So this is an advection diffusion equation. All right, but we now have to put this spatial operator in Sturm-Liouville form. And so no big deal. That was what chapter 3 was all about. So let's do that. LU equals UXX plus UX. And the way I'm going to find the weight function is I'm going to, actually, let me erase that. 1 over W, WUXX plus WUX. Okay, and I want the derivative of this thing multiplying the UXX to equal this thing multiplying UX. And so I get W prime equals W. And that we have seen before, that has e to the x as the weight function. Okay, so I have found my weight function. It doesn't really help me solve the problem at all, but for completeness, I could say that I could put this in Sturm-Liouville form, 1 over e to the x, e to the x, ux, x. Okay, there's my operator in Sturm-Liouville form. And now that I've put it in Sturm-Liouville form and found the weight function, I know that the eigenfunctions will be orthogonal under that weight function. I know that the transform of the operator will be minus lambda sub n u sub n and all the other good things. Okay, so next, find those eigenfunctions. The eigenfunctions are going to satisfy phi xx equals minus lambda phi. And with, no, I'm sorry. That's not true at all. Phi xx plus phi x equals minus lambda phi with phi of 0 equals 0 and phi of 1 equals 0. And so if I guess e to the rx, then I get r squared plus r plus lambda equals 0, or r equals -1 plus or minus the square root of r squared plus or minus the square root of 1 minus 4 lambda over 2. And this is why I should have let v equals 2. But JC, what did I forget to do? I forgot to split the problem, didn't I? Good. Non-homogeneous boundary conditions mean that I cannot, they don't play well with eigenfunctions. So that's an excellent question. Would it not be phi of 0 equals 1,000? And that would not go well if we had a non-homogeneous boundary condition in that eigenfunction problem. So absolutely, we split that out with a boundary solution. What equation do we want our boundary solution to satisfy? Just like before, we want it to satisfy L UB equals 0. What is LUB? It's UBXX plus UBX equals 0 with boundary conditions UB of 0, T equals 1,000, and UB of 1, T equals 0. Actually, did I write this down? I did. Yeah, okay. Yeah, that's fine. All right. Okay, and so how do we go about finding the solution to this problem? It is a constant coefficient, second order ODE, and we can guess a solution. We can guess UB equals e to the Rx, and that's going to give us R squared plus R equals 0, R equals -1 and 0. And so UB of X. Note that this is not, plus or minus something. So it's not necessarily Cauchy Cinch, which would be my favorite basis. Since this is just two different numbers, R equals -1 and R equals 0, then I'm just going to write down as my solution C1 e to the minus X plus C2. Okay, now I satisfy my boundary conditions. UB of 0 is going to be C1 plus C2. And that has to be 1,000. And UB of 1, technically we've got and then technically these depend on time. But as we'll see, there's no time dependence in the boundary conditions, and so these are end up going to just be constants. UB of 1 comma t is going to be C1 of t e to the -1 plus C2 equals 0. Okay, and we solve this 2x2 system for the values of C1, C2, and we have our boundary solution. I'll leave that to you. All right, now, because I've had my boundary solution, my interior problem is going to have homogeneous boundary conditions. What I really want to focus on today is finding these eigenfunctions and showing how to combine the Sturm-Liouville with the diffusion equation. So here are R's. We have, in principle, 3 cases. What's the dividing case here?
lambda equals 1/4.
Yep, lambda equals 1/4. Okay, and so I'm going to consider the case lambda greater than 1/4. And in that case, this is negative. I can pull out a minus sign as an I. I get R equals -1/2 plus or minus I square root of, what I'm going to do is pull out a factor of 4 from the square root, which cancels the 2, and I'm going to be left with lambda minus 1/4. Okay, and so what are the eigenfunctions here? They are e to the -1/2 x, e to the plus or minus I square root lambda minus 1/4 x. All right, this just is what it is. It doesn't turn into anything, but e to the plus or minus I turns into sines and cosines. And so our eigenfunctions are, and I'll write these on the next page. E to the -1/2 x cosine square root lambda minus 1/4 x plus C2 e to the -1/2 x sine root lambda minus 1/4 x. Can you go back for a second? Yes. I think, yeah, C1. I think I'm up to date on posting the PDFs of these lectures. They're in a folder on Canvas called, I think they're called like lecture notes or something. But they should all be in there for the last 5 lectures or so. Okay, and now we satisfy our boundary conditions. Phi of 0, sine of 0 is 0. That's a good question. And the answer is I'm not entirely sure. I really want it to be true that the Rayleigh quotient rules out values of lambda less than the dividing point. But I'm not sure that that is true. If P is positive and Q is negative or 0, then it's definitely true that you don't have any negative eigenvalues. I just don't know if it keeps you from having to check that little sliver of space in between 0 and the dividing case. So it's an excellent question. I'm sorry I don't have the answer. Yeah. Sure, I can do that. And so in this case, I'm only going to consider lambda greater than 1/4. Typically, you don't get typically the only time you get that dividing case is if you have purely Neumann boundary conditions. That's typically the requirement to get that extra eigenfunction. And I don't know that I've ever seen a problem where you get eigenvalues below the dividing point. Which is what makes me want it to be true that if you knew how to manipulate it, the Rayleigh quotient would tell you that there are none, because I've never seen one. But I just don't know for sure. I played around with it a little bit, and it's like more complicated than I thought it might be, and it would take me a whole class to show it, and we might have to know some variational calculus. And so anyway, that's what we can do is on a test. I can just tell you that. So phi of 0 is 0. Sine of 0 is 0. So this term does not contribute to phi of 0. This is just going to give us C1. All right, and that has to be 0. So this is not going to be present in our eigenfunctions. And then phi of 1 is going to be C2 e to the -1/2 sine of the square root of lambda minus 1/4. Okay, and all the standard arguments apply. We don't want C2 to be 0. E to the minus a half isn't 0. And so we want the square root of lambda minus a quarter to be one of the roots of sine, which are n pi. Okay, and that gives us that lambda n equals a quarter plus n pi quantity squared, and phi sub n equals e to the minus a half x sine n pi x, where n goes from 1 to infinity. All right, so we're almost there. We only have 4 minutes left, but we should be fine for me to show you what I want. We've now found the eigenfunctions. We know that the weight function is e to the x, and you can see that if we multiply together two different phi's, e to the minus half x's will combine to an e to the minus x, which will be canceled by e to the positive x, and so we'll get that nice orthogonality result. If I now transform the PDE, okay, and now I have my, my interior solutions will be whatever they are, and I'll have some modified initial condition that comes from the boundary. It would be 0 minus u boundary of x. Okay, but what I really want to get to is that when I take the transform of this, I don't take the transform of each term and try to figure out what's the transform of this and what's the transform of that. Okay, because the whole point, and this is just like boundary problems in chapter 3, this is the operator. This whole thing is the operator, and it's the transform of the operator that is minus lambda sub n u sub n. Okay, and so after we take the transform, even of this weird advection diffusion reaction or advection diffusion equation, we get exactly the same thing that we get with a normal diffusion equation. No matter how complicated I make this right-hand side with different spatial terms, as long as I find the eigenfunctions of that spatial operator, the transform of this problem is always going to be this. Okay, and so I'm always just going to have to solve some ODE and then, satisfy the initial condition and invert the solution. So I'll have uin of 0 is going to be negative transform of ub of x. And whatever that solution is, I'm going to have to take its transform, and that's going to be the initial condition here for this ODE. So even this last problem, homework problem 4, you can view through the lens of chapter 3 and say that, any diffusion type equation, I can just focus on the spatial part and put the spatial part in Sturm-Liouville form, find the weight function, find the eigenfunctions, take the transform, and no matter the time derivative, no matter the form of the Sturm-Liouville problem on the right, the Sturm-Liouville operator, I'm going to get a fairly simple ODE to solve. And yeah, that's a little bit harder than simply dividing by lambda. Life is not always easy, but I solve that ODE and I carry on my way. Do we check Sturm-Liouville form on original problem or U interior? Technically, it only matters that U interior is in Sturm-Liouville form and is self-adjoint. But the structure of the problems are so similar, they have the same spatial operator, that you might as well identify the operator and put the operator in Sturm-Liouville form at the very beginning. Technically, you don't have to do it until you get to the interior problem, but there's no real advantage in waiting. U interior ends up being original problem anyway. Yeah, it's the same operator, right? Your interior problem is always going to be, once we split this, it's going to typically be ut interior, u interior of time, L acting on u interior plus f, the forcing function. All right, and so the interior problem is going to have that same spatial operator as the original problem. And so there's, like I said, there's no benefit to waiting until you've obtained the interior problem. I would even argue that because the central idea and the central tool of this class is finding the transform, and the transform is a property of the operator, of the spatial operator, it sort of makes sense to do that first, right? Because it's the most important thing. And so as soon as you're given a problem, you might as well, as soon as you're given a diffusion problem, you might as well say, well, okay, what's the spatial operator and how do I put it in Sturm-Liouville form to guarantee that everything's going to work? We only apply W to the transform. Well, W it becomes part of our definition of the inner product. All right. Now, yes, the transform is the primary thing that uses the inner product. Technically, the definition of self-adjoint relies on that inner product with W in it. The projection formulas, also rely on that inner product. But of course, the projection formulas are just another way to describe the transform. So if W is 2, we don't put the 2 in oh, you're talking about the other homework problem. That's a good question. You guys are free to go, I understand, if you've got somewhere to be, but I'm happy to keep answering questions as usual. You're thinking about this problem where we had ut equals 2 uxx. And so yes, technically L acting on u equals 2 uxx. But W is not 2 here. If we really wanted to carry through, let's put it in Sturm-Liouville form. Okay, 1 over W, 2 W uxx plus 0 W ux. We want the derivative of this to equal this. We would get 2 W prime equals 0, W prime equals 0, W equals a constant, an arbitrary constant. And because of the way the weight function works, it doesn't matter what the constant is. You can multiply the weight function by any constant and you still get a valid weight function. Okay, and so we might as well just say W equals 1. Here's why that doesn't matter. When we're taking the transform of something, right, we are taking an integral from 0 to L of something times phi sub n times W dx divided by the integral from 0 to L of phi sub n times W dx. Well, if I multiply W by a constant, I can pull that constant out of the top integral and I can pull that constant out of the bottom integral and they cancel, right? And they don't change the value of the transform. So even though the operator is 2 uxx, the weight function is still just 1. And it's already in Sturm-Liouville form.
But I'm saying that, like, whenever you're finding the eigenfunctions, like if you do find a value of W, it doesn't change like your phi, right? Like you the first time you apply W is in the transform, right?
Oh, yes. Yes, yes. What the function that you find for W does not change your eigenfunctions, and it does not change how you go about finding your eigenfunctions.
Okay, cool.
Because your eigenfunctions just satisfy L phi equals minus lambda phi, and you solve that ODE, and there's no W to be found in here.
Thanks.
Yep. Any other questions? Yeah. Yeah, technically the eigenvalue problem here is 2 phi xx plus lambda phi equals 0. What you'll find is that it doesn't change the eigen functions. You'll get the same eigen functions even if you forgot to keep the 2 in there. And in fact, it actually, I'm just going to say yes, because if I say, well, technically you can get away with forgetting the 2, then you run into trouble if you're doing, say you're doing something like this. All right, now you can't just drop one of those constants. So you know what? I'm just going to stop talking and I'm going to say, yes, this is the eigenfunction problem. No problem. I will work on finishing my homework 3 solutions and post them as soon as I can. I'd like to do it today. I have another thing that I promised would be done by this afternoon. So I'll see if I can do them both. Yes, I will post the homework 4 solutions right after you turn them in at 11 o'clock on Monday.